Hello and welcome to my talk about minimizing the cumulative batch processing time for an industrial oven scheduling problem. This talk is based on joint work together with my colleagues Christoph, Nysret, Daniel and Felix, and we work together in the Christian Doppler Laboratory for AI and optimization for planning and scheduling. Now let me start by telling you in which area the oven scheduling problem that we study occurs. So when manufacturing electronic components, many components need to undergo a hardening process, which is done in specialized heat treatment ovens. And running these ovens is very energy intensive and thus costly. So we want to reduce the time such ovens need to be run. And in order to do so, we group jobs that can be processed simultaneously together in batches. And if I say simultaneously, I mean that jobs in one batch need to enter the machine, the oven, at the same time and need to leave the machine at the same time. So we cannot interrupt the heat treatment and remove or add some items to the oven. And the challenge here in finding a schedule of jobs to machines and to batches is that many constraints need to be fulfilled, and also that we want to minimize an objective function that consists of various components. So what are these constraints that we need to fulfill? Well, every job has an earliest start time and may not be processed before this point in time. Every job also has a minimum and a maximum processing time, and the processing time of a batch must lie between this minimum and maximum if the job is contained in this batch. Also, machines are not available all the time. Every machine has a calendar which is specified by availability intervals, and every batch needs to be scheduled entirely within one of these intervals. Also, every machine has a maximum capacity that may not be exceeded, and every job has a size that contributes to the size of a batch. And we're only allowed to combine jobs in the same batch if they have the same attribute. And this attribute can be thought of the temperature or the program at which a job is treated in the oven. And we're only allowed to combine jobs that are heat treated in the same way in the oven. Also, jobs cannot necessarily be processed on all ovens. For every job, a set of eligible machines is given. And we do not only want to find a feasible assignment, we want to find an optimal assignment of jobs to machines and an optimal schedule. First of all, we want to minimize the cost of running ovens. And running an oven does not depend on how full the oven is, it only depends on the processing time. So what we want to do is minimize the cumulative batch processing time. So ideally, we would batch jobs together as much as possible. But at the same time, we also need to respect the job's due dates, and there are various ways of doing so. Here in this application, we decided to minimize tardiness by minimizing the total number of tardy jobs. We also need to find a sequence of batches that minimizes setup times and costs. So between batches, setup times and costs are incurred. So why is this? Well, if we have one batch that treats jobs at a certain temperature and the next batch at another temperature, then there will be a time for heating up or cooling down the oven in between. And also there are setup costs between batches that are not necessarily correlated with the setup times, and these are costs that are related to personnel that need to empty or fill the ovens, need to clean the ovens, and so on. And we want to minimize both the cumulative setup times and the cumulative setup costs. This defines the oven scheduling problem and makes it belong to the class of batch scheduling problems, which have vastly been studied in the literature. There are thousands of papers devoted to these kinds of problems, and many different variants have been studied. But what makes the oven scheduling problem different to other problems is, on the one hand the objective component concerning the cumulative batch processing time. This is an objective that, to the best of our knowledge, has not been studied yet in the literature, and also the combination of special constraints that we have here has also not yet been studied. Now let me show you a small example. So given a scheduling horizon, so this is the length of the time window in which we are planning, we're given a set of machines. So here we have two machines with maximum capacities and intervals during which the machines are available. We also have two attributes, and the setup times and setup costs are given by a 2x2 matrix. So the entry 2 in here, for instance, stands for the setup cost when switching between a batch of attribute 1 to attribute 2. The setup time, sorry. And then we're given a set of jobs, so 6 jobs here with eligible machines, earliest start times, latest end times, minimum and maximum processing times, sizes, and one of the two attributes. Now let's have a look at the visualization of this example. Here we have the two machines where the dashed lines correspond to the maximum capacities. The dark gray areas are the time intervals where the machines are not available. And here we have the 6 jobs. The two colors represent the two different attributes. And jobs can be processed after this leftmost border of the rectangle and need to be finished before the tip of the arrow. This lighter area here represents the time between the minimum and maximum processing time, and the height of the rectangle corresponds to the size of the job. What could a feasible assignment look like? It could be something like this. So we have a schedule with 3 batches, 2 on machine 1 and 1 on machine 2. And with the objective function that I will define shortly, this is actually the optimal solution for this instance. So let me now turn to the constraint programming model that we developed for the oven scheduling problem. And the first question that we needed to answer is how to model batches. Well, in the worst case, we will need 1 batch per job if jobs cannot be combined in batches. So in the worst case, we will need n batches. And it might also be possible that all these batches need to be scheduled on the same machine. So therefore, we define the set of potential batches where batches have 2 indices. The first index indicates the machine it is on, and the second index the batch number on this machine, and where the batch number can be between 1 and the number of jobs. And in order to break symmetries, we decided that the batches are sorted in ascending order of their start times. So B11 will be before B12, before B13, and so on. Also, there will be lots of empty batches. In total, we will at most need n batches, and all others will remain empty. And we will force empty batches to be scheduled at the end of every machine. Okay, now what are the decision variables that we use to model our problem? We have one variable that indicates the machine a job is assigned to. This is mj, and the batch number a job is assigned to, which is bj. And together, these two variables uniquely characterize the batch a job is assigned to. So this would be b index bj mj. And we have another variable that encodes the start time of a batch, SMB, which is in the interval 0L, and another one for the processing time of a batch, so PMB, which is in the interval 0 to the maximum overall processing time of any job. Also, to formulate the constraints and the objective function, we need some auxiliary variables, the attribute of a batch, the availability interval for a batch, so every batch needs to be scheduled entirely within one availability interval on the machine it is assigned to, which we denote by I and B. and then the number of batches per machine, which we denote by Bm, which means that a batch with batch number higher than Bm on this machine necessarily is empty. Now, using these variables, we can give a formal definition of the objective function. So we have the four components I mentioned earlier. The cumulative batch processing time. This is simply the sum of all processing times, where the processing times of empty batches are set to 0. The number of target jobs is equal to the number of jobs for which the start time of the batch they're assigned to plus the processing time of the batch is greater than the latest end time. And the cumulative setup times are given as the sum of setup times between consecutive batches on the same machine, so setup times from attribute MB to attribute MB plus 1, where ST stands for the matrix of setup times, and the same for setup costs, where SC stands for the matrix of setup costs. And we want to combine these four components of the objective function in a single function. And there are several different ways of doing so, but in order to remain flexible and to be able to give weights to all the four components, we decided to do this in a linear combination. And for this purpose, we first normalized the four components such that their values are between 0 and 1, and then they're multiplied with weights alpha, beta, gamma, delta in order to obtain the cumulative objective function, which then has a value between 0 and 1. We also defined two alternative models. First of all, an ILP model, which as the CP model we implemented in Minisync. And the main difference here is that instead of using variables mk for the machine and bj for the batch number, we use binary variables with 3 indices, x, m, b, j. So this variable is equal to 1 if job j is assigned to machine m and batch b on this machine m, and 0 otherwise. As before, we have integer variables smb and pmb that encode the start and processing times of batches, and we linearized all the constraints that I mentioned earlier in my talk using some auxiliary variables and big M. We also developed a CP optimizer model, which makes use of interval variables for the batches. So the interval variables are given by the start and end time of a batch, and these are optional interval variables as we define as before b and b for all possible values of m and b, and only at most n of these batches will actually be used. And whenever a batch is present, a setup time before this batch will also be incurred, and a corresponding interval variable for the setup time is also defined. Moreover, we make use of an intensity function to encode the machine availability times, and we use several global constraints on the interval variables. Now let me turn to the experimental evaluation of our methods. So in order to assess the quality of our methods, we created a set of 80 benchmark instances, and for this purpose we designed a random instance generator with 15 different parameters. And first we created a very large set of instances with over 16,000 instances for 10, 25, 50, and 100 jobs, 2 or 5 machines, and 2 or 5 attributes. And for every one of these 16 combinations of numbers of jobs, machines, and attributes, we randomly selected 5 instances, which results in a set of 80 instances. So we have 20 instances each with 10, 20, 50, and 100 jobs. And it turns out that all 80 benchmark instances are actually satisfiable and can be solved by a simple construction heuristic. So this construction heuristic orders the jobs by their earliest start dates and assigns jobs to available and eligible machines. And then once a job is scheduled, checks if there's any other job that is available at that time that can be added to the same batch. And if not, continues with the next point in time. And that the instances are satisfiable and solvable by greedy heuristic is actually this actually reflects our industrial application, because there it is also the case that it is not hard to find feasible solutions. It is hard to minimize the cost of feasible solutions. For this benchmark set, we conducted experiments with 53 different combinations of models and methods. So the CP and ILP models that I presented briefly are implemented in Minisync, and we used recent versions of Chuft, OR tools, CP Optimizer, and Gurobi to solve them. For Chuft, OR tools, and Gurobi, we also tried 7 different search strategies. And with Gurobi, we also investigated a warm start approach, which uses the construction heuristic to find an initial solution, and then this solution is provided to the Minisync model as a starting point. The OPL model with interval variables was run using CP Optimizer. For every instance, the time limit was set to 1 hour. And all our experiments were run on single cores, and we used a computing cluster to conduct these experiments. So let me show an overview of our results. So the bold figures show the best results per column. So we can see that Gurobi with the warm start approach could solve all 80 instances, and without the warm start approach, Gurobi could solve less instances, but OR tools with the ILP model could solve all but 2 instances. The best results and also the most optimal results and optimality proofs were again provided by Gurobi ILP with the warm start approach, followed by Gurobi ILP without the warm start approach. And if we look at the proof time for optimality proofs, the most fastest proofs could be provided by Gurobi ILP without warm start approach. Now, if we have a closer look at the proof times, here in this figure we compare proof times for those 13 instances where all solver method combinations could find optimal solutions within the time limit. And here we can see that clearly OR tools and Gurobi outperform Chuft and CP Optimizer, and OPL lies somewhere in between these two extremes. For those instances where we could not find an optimal solution, one can have a look at the optimality gap in order to assess the solution quality. So for solvers such as Gurobi, one also obtains dual bounds, so lower bounds on the solution cost, and this allows us to define the optimality gap. So the gap is 1 minus the best dual bound found divided by the current best solution found. And if the optimal solution has been found, then this gap is equal to 0. And here in this graph, we display the optimality gap for the overall smallest gap per instance, so the smallest gap across all solvers and methods. And we can see that generally the gap increases with the size. But this is not the only explanation that we can give for the size of the optimality gap. So we can see that for instances with 10 or 20 jobs, the bound is tied for almost all instances. But also for instances with more than 50 jobs, there are still in total 15 for which the gap is less than 1%. So these are very good results. Finally, let me have a look at the warm start approach. Just quickly, we can see here that the heuristic solution could be improved for all 80 instances. And The solution quality of the solution found by Gurobi without warm start could be improved for 12 instances. However, for 6 instances, the solution quality was worse than without warm start. And we could also, with warm start, find slightly less optimality proofs than without warm start. So let me sum up very briefly. Using our models as well as the warm start approach, we were able to find feasible solutions for all 80 benchmark instances. And for 50 of the 80 instances, the best optimality gap is less than 1%. And overall, the best results were found by Gurobi and our tools with the ILP model. In the future, we would like to improve the solution quality for large instances by developing mid-heuristic strategies and also perform an in-depth instance space analysis in order to explain which parameters cause instances to be hard. Thanks for your attention.